Welcome to one more optimization example. So in this example, a child can kick a ball off the ground at 40 feet per second. If the ball leaves the ground at an angle of theta, the height of the ball t seconds after leaving the ground is given by h equals negative 16t squared plus 40 sine theta t. So we have our height, putting it back into just theta. Height is equal to negative 16t squared plus 40 sine theta times t. And then the distance that the ball will travel before it hits the ground is given by d equals 40 cosine of theta times what I'm labeling as capital T. And capital T is the time the ball is in the air, or the time it takes for the ball to hit the ground. And so we are wondering what angle will maximize the distance traveled. So again, this is height and the distance traveled. So this is actually the equations for this. Those of you who have taken some physics may have seen a similar scenario. Essentially, here's the ground. You start with a ball here, and it gets kicked at an angle of theta. Now, gravity is going to push that ball, slow it down its rise, and then ultimately make it fall. So the ball itself will more travel a parabolic path. And if the ball is going at 40 feet per second this way, it turns out that its horizontal velocity or horizontal speed will be 40 cosine theta, the horizontal sort of component, if we broke that down. And then the vertical component will be that 40 sine theta you see in the height equation. So we're labeling this distance as d, and then capital T is the time elapsed, and then height is however high up the ball is at whatever point in time. So if we want to figure out, we need to know that capital T to do our optimization, and then we also have some limits on our theta. So some limits. Where presumably the ball is going to be between 0 and 90 degrees. So we have 0 degrees is less than or equal to theta is less than or equal to 90 degrees. Or equivalently, we'll have 0 radians is less than or equal to theta is less than or equal to pi over 2 radians. So we might kick the ball straight up in the air, and we'll have 0 distance then, but we're not going to kick it backwards, nor will we kick it underground. So these are our limits. We can go ahead and solve for capital T. So that happens when the height equals 0. So this occurs when h equals 0. And so we can go ahead and set our h equal to 0. We have negative 16t squared plus 40 sine theta t. Both of those terms have a t in them. They also both have an 8. So we could go ahead and factor out a negative 8t. And we would be left with 2t minus 5 sine of theta. And so we either have t equals 0, which is when the ball is kicked, or 2t minus 5 sine of theta equals 0, which will be when it lands. And so we wind up getting here that t is equal to 5/2 sine theta. And this is the one we want. So this will be our capital T. This is when the ball lands. And so what we have then is we want to maximize distance and we get, again, distance was equal to 40 cosine of theta times that capital T, or 40 cosine of theta times 5/2 sine of theta. And this is 100 cosine theta times sine of theta. And I'm going to use a little trig identity manipulation here, just to make my life easier. So recall that sine of 2 theta is 2 cosine theta sine theta, or sine theta cosine theta, whichever way you want to read it. And so 100 cosine theta sine theta would be 50 times 2 cosine. So we have d equals 50 times 2 cosine theta sine theta, or d equals 50 times sine of 2 theta. You certainly do not need to do this to solve the problem, but it may make your life a little bit easier. So from here, again, we know that theta falls between 0 and pi over 2. And so from here, we can go ahead and do our optimization. So we have the derivative d prime with respect to theta. We will have 50 cosine theta, sorry, cosine of 2 theta. It's that derivative of sine is cosine. And then chain rule, we should multiply by a 2, since the derivative of 2 theta is 2. So we're really looking at 100 cosine of 2 theta. And then we want to know where this is equal to 0 or undefined. So cosine is never undefined. And cosine is equal to 0 at, cosine is on the unit circle is the x coordinate, right? And so cosine equals 0 when we're at the top or on the bottom. So this would mean that 2 theta is equal to pi over 2. And that's the only, sorry, it could be pi over 2 or 3 pi over 2. We could keep going if we wanted, but we do have our limitations. So we get that theta is equal to pi over 4 or 3 pi over 4. 3 pi over 4 is outside of our limitations. So this is outside 0 less than or equal to theta less than or equal to pi over 2. And so our point of interest will be at theta equaling pi over 4, as well as our endpoints. So our points of interest at theta equals 0, pi over 4, and pi over 2. So from here, we are going to go ahead and evaluate our distance evaluated at theta at each theta equals 0, pi over 4, and pi over 2. So again, we'll have our theta and our d of theta. We're looking at 0, pi over 4, pi over 2. And distance of theta, again, remember our distance was 50 times sine of 2 theta. So we are looking at 50 times sine of 2 times theta. So d of 0, we're looking at 50 times sine of 0, which is 0. At pi over 4, we are looking at 50 times sine of pi over 2, which that sine is 1, so we get 50. And then if we evaluate at pi over 2, once again, we get 0. Now, in reality, you can kick a ball so it rolls along the ground, but we're ignoring that particular situation, so it's going up in the air. So what we wind up getting then is our maximum, our optimal situation is at this pi over 4. So we get that the maximum distance is 50 feet, which occurs when the angle is pi over 4 radians, or in other words, 45 degrees. So this is our the angle that the child should kick the ball at, so it travels the maximum distance. This 45 degrees is pretty uniform no matter how fast you're kicking the ball, or how fast an object is leaving. If it's just from, if it's the height it's taking off at is the same height as where it lands, then this 45 degree angle will be the optimum angle for getting the max distance.